Hello everyone, my name is Rakshita M. I'm from Sri Venkateshwar College of Engineering, Department of Electronics and Communication Engineering. Today I'm going to discuss about the subject called digital communication. In this today I'm going to discuss about the state and proof properties of Fourier transform. Now let us see what is Fourier transform. Fourier transform is a mathematical model which helps to transform the signals between two different domains, such as transferring signal from frequency domain to time domain or vice versa. Fourier transform properties. The important properties of Fourier transform are duality, linear transform, modulation property, and Parseval theorem. Duality. It shows that if h of t possesses a Fourier transform h of f, then the Fourier transform related to h of t is h of minus f. Linear transform. Fourier transform comes under the category of linear transform. Let g of t and h of t be two Fourier transforms which are represented by g of f and h of f respectively. In this scenario, it is easy to find the Fourier transform of the linear combination of h and g. Modulation property. As per the modulation property, functions are modulated by the other functions if they are multiplied in time. Parseval theorem. As per this concept, the Fourier transform is unitary. This implies that the sum total of squares of its Fourier transform h of f is equal to the sum of squares of the function h of t. Now, now let us see how does the Fourier transform work. As we are only concerned with digital images, we will restrict the discussion of the discrete Fourier transform. The DFT is the sample Fourier transform and therefore does not contain all frequencies forming an image, but only a set of samples which is large enough to fully describe the spatial domain image. The number of frequencies correspond to the number of pixels in the spatial domain image, that is, the image in the spatial and Fourier domain are of the same size. The Fourier transform is an important image processing tool which is used to decompose an image into its sine and cosine components. The output of the transformation represents the image in the Fourier or frequency domain, while the input image in the spatial domain equivalent. In the Fourier domain image, each point represents a particular frequency contained in the spatial domain image. The Fourier transform is used in a wide range of applications such as image analysis, image filtering, image reconstruction, and image compression. These are the list of the Fourier transform properties: linearity, time shifting, differentiation, integration, time scaling and time reversal, frequency shifting, duality, time convolution, Parseval theorems. Now, let us move to a first property. Time shifting property states that a shift of t naught in time domain is equivalent to introducing a phase shift of minus omega t naught in frequency domain, but amplitude remains same. And this is the equation of the time shifting property. And by doing the Fourier transform, we get this equation. Next, we shall move towards the next property, differentiation. Differentiation in time domain corresponds to multiplying by j omega in frequency domain. This is the differentiation property in time. By doing the Fourier transform, we get this equation. And this is the differentiation property in frequency domain. And we get this equation by doing Fourier transform. The time integration property states that integration of a function x of t in time domain is equivalent to the division of its Fourier transform by a factor of j omega in frequency domain. This is the final expression we get by performing the Fourier transform to the given time integration. The next property is time scaling and time reversal. The time reversal property of a Fourier transform states that if a function x of t is reversed in time domain, then its spectrum in frequency domain is also reversed. Now, uh, this is the given equation, and this is the time shifting equation. By performing the Fourier transform on these two equations, we get the required time scaling and time reversal property, that is e power minus j omega t naught into x omega. The next property is frequency shifting property. Frequency shifting property of a Fourier transform states that the multiplication of a time domain signal x of t by an exponential, that is ej omega naught t, causes the frequency spectrum to be shifted by omega naught. Therefore, if x of t upon Fourier transform gives x of omega, then according to the frequency shifting property, ej omega naught t x of t upon the Fourier transform, we get x of omega minus omega naught. By performing Fourier transform these two equations, we get the desired frequency shifting property. Now the next property is duality. The duality property tells us that if x of t as a Fourier transform x of omega, then if we form a new function of time that as the functional form of the transform x of t, it will have a Fourier transform x of omega that is the functional form of the original time function, but is a function of frequency. This is an example of the duality property, and this is the proof of the duality property. The next property is time convolution. According to the convolution property, the Fourier transform maps convolution to multiplication. That is, the Fourier transform of the convolution of two time functions is the product of the corresponding Fourier transform. And here we have done the proof of the time convolution. The next is Parseval's theorem. Parseval's theorem states that the energy of a signal in time domain is equal to the energy of the transferred signal in the frequency domain. Preservation of this equality is the underlying reason why the spectrum is normalized by 1 by n in equation. And this is the proof of the Parseval's theorem. Thanks for watching my video.